So the second lecture in the course would be, and the third lecture would be about cryptographic preliminaries. So why do we need so much cryptography before we can even start talking about blockchain? Well, because it's used in blockchain for many different purposes. It's used to encrypt data. It's used to prevent unwanted modifications. So the immutability or resilience to tampering of the blockchain structure is due to use of cryptography. When you propose new blocks, there are many consensus algorithms, and some of them are heavily relying on cryptography, such as proof of work. So in proof of work, in order to gain the right to propose a block, you need to solve a crypto puzzle, and that requires, so what is a crypto puzzle? In order to understand that, and in order to understand why it works, you need to have a background in cryptography. When executing transactions need to be verified, and general data need to be verified, and the verification is due to signatures and cryptographic data structures. So cryptography again. And sometimes in order to verify the inclusion of a transaction in a block, you use data structures, cryptographic data structures such as Miracle Tree, which are also based on cryptography. So that's why. I'm not going to, this is not a course in cryptography, I'm just briefly covering the relevant cryptographic primitives and parts. So in blockchain, we are mostly using asymmetric cryptography with the public key and the private key. The idea was conceptualized by Diffie and Hellman in 1976. So in asymmetric cryptography, there is a pair of keys, one public, one private. And for example, Alice can sign messages with her private key, while everyone else can verify that indeed it was Alice who wrote the message by using the public key of Alice. Public key verifies. The other use is that everyone can encrypt the message to Alice with her public key, but then only Alice will be able to decrypt it and read the message, no one else. So the use of public cryptography in blockchain is so typical because the blockchain is not based on one-to-one interaction, where say, symmetric cryptography might be more applicable. In blockchain, you have, for example, one sender of the message, and then the entire world would be welcome to check the ledger and verify the transaction. So hence the need for asymmetric cryptography. Okay, so asymmetric cryptography, we need a key pair. How do we generate a key pair? What are the requirements? Well, the construction of the pair needs to be fast. It should be fast when we use the key, when we encrypt, or when we sign messages, and when we verify. That the usage of the keys must be fast. And that means that the keys need to be short. So of course, the shorter the key, the faster it is, but it's less secure with the shorter key. It's easier to guess the key if the key is short. So there is a trade-off in terms of the key length. And of course, the other requirement is that guessing the private key based on the public key needs to be hard. How do we achieve this hardness? How do we construct the keys? So the hardness of guessing the public key is due to the existence of what's called one-way functions. And again, there is heavy math involved, but I'm just giving an overview. The gist of the one-way functions is that they're fast to compute, but it takes a lot of time to inverse the function. It's hard to inverse the function. So several ideas have been proposed, like regarding which one of a functions to use. The first idea was the RSA function proposed in 1977. Today, most of the ideas are based on the problem which is called generalized discrete log problem. What's the problem? We are given a finite cyclic multiplicative group. Okay, I'll immediately give a realistic example. So we could create a group of natural numbers or remainders of division by certain primary integer. So, for example, 7 or 11. How would we form such a group? The group would consist of all the natural numbers from 1 to 6. If the primary number used to generate the group is 11, then it would be all natural numbers from 1 to 10. Okay, so what's the operation? The operation is multiplication. The group is multiplicative. So, for example, if we want to take a multiplication of 5 and 7, group up to 7, so let's take 3 and 4. 3 times 4 is 12, but we compute the remainder of 7, so it would be 5. The multiplication of 3 and 4 is 5 in this group. That's the operation. Now, why is it cyclic? Cyclic means that there is a generator number. In the case of the group of 7, it would be 3. So we can, 3, what is the generator number? It means that we take the generator number and put at different degrees, square, to the third, to the fourth, and so on. And this way, we are able to generate all members of the group. So for this group of created by the prime number of 7, the generator would be 3, and 3 to the second 9, 2, 3 to the third 6, 3 to the fourth 4, 3 to the fifth 5, 3 to the sixth 1, and 3 to the 7 is 3 again. So we exhausted all the members of that group. And this is why the group is cyclic. And actually there is a theorem saying that if the number is primary, then any group created this way would be cyclic and would have a generator. Okay, so that was an exemplification of the cyclic multiplicative group. But what's the problem of the discrete log? The problem is the following. We take any two members of the group, and the problem is to find the logarithm of one element based on the second element. For example, given 1 and 3, we need to find the degree to which we need raise 3 in order to get 1. Okay? So in this group, it happens to be equal to 6, as we see, because 3 to the 6 is equal to 1. But the problem is to how to find it at 6. That's the problem. So which one? Yeah. 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 3 to the 3 is okay. 3 to the 3 is 27, right? 27 divided by 7 is 6. The remainder is like it's 21. 27 minus 21 is 6. The remainder is 6. They are computing remainders. Okay. Okay, so that's the idea. Now let's see the application. So how do we do it? How do we construct the keys? So how do we build a cryptographic public key cryptography based on this problem of generalized discrete log? Okay, so the group and one member of the group are selected a priori and known to everyone in the world. So, for example, we know that it's a group of numbers of 1 to 6. Well, this is, of course, a very small group. The practical group would be much, much bigger. But anyway, the group is known a priori, and we pick one member of the group, such as 3, a priori, beforehand. And we make sure everyone knows what they are. Now, suppose Alice wants to generate her own key pair, the public key and the private key. What does she do? Alice picks a random number k, which becomes her private key. Then Alice takes, calculates b to the degree of k. Okay, how would and a becomes your public key. Now, how can Alice calculate a efficiently? How can Alice calculate b to the degree of k efficiently? Well, the naive algorithm would be to take b and just multiply it k times. But that would require k multiplications, and k can be very big in practice. So that's a lot of operations. We don't want that. What would be a faster way to calculate b to the degree of k? Yeah, I mean, it's just it's a simple. It's like well, it's not exactly a binary division, but what you do is that you divide k by half, and you calculate sort of square root of b to the k, and then if you know how to calculate the square root of b to the k, then we can calculate the square just in one operation, and then we take k by half. Okay, how do we calculate to the degree of k by half? We calculate b to the degree of k by 4. And again, calculate the square. And this way, instead of doing k multiplications, they are doing logarithm of k multiplications, which is much faster. So this is why generating the public key is efficient for Alice. Okay, now, how difficult would be for an attacker? So what is the attacker given? The attacker is given A, and of course everyone knows G and B. How difficult, how hard would it be for the attacker to restore K? To hack the system and figure out what the private key K is? Let's see. So the brute force algorithm is so we have B, we have A, and we have G. What can we do? Well, we can just take B and start multiplying it by itself. To the second, to the third, just a brute force. That would take a number of operations which is linear with K. Because the attacker doesn't know K. The attacker cannot do this trick which Alice did. The attacker cannot divide K by half and get number of operations which is logarithmic with K. The attacker needs to do it in a linear way. And that's much more inefficient. So in practice, against the brute force attack, a key length of, say, binary key of length 80 bit is considered, again, already secure because 2 to the 80 operations is already a large number that, say, for a common user, for a common hacker, it's already difficult to break. Okay, but is brute force the best the attacker can do? Can the attacker do better than brute force? So the best known algorithm for calculating K, if we know A, B, and G, so best known algorithm that work for an arbitrary case would take an order of the square root of the size of G. So not linear with G, but a square root. Still, square root is much, much bigger than logarithm of K. So it's still much harder for the attacker to figure K than for Alice to calculate the public key. So square root means that in order to be secure in practice, you need a key maybe of length 160 bit instead of 80 bit. So twice the number because of the square root. So that's the general idea. Now, okay, so so the general discrete log problem. There are still questions remaining. In practice, what group should we take? I mean, I was showing you the case of division by 7, right? The group which is generated by the primary number of 7. In practice, of course, this is way too small. This is just to illustrate the concept. Okay, so what would be practical? What would be a good group to use in practice? So there are different proposals. Early proposals, and perhaps still the most popular case today, is to use such groups based on primary numbers. But of course, instead of 7, we'll be maybe taking like numbers order of 2 to the 80, right? But we still need a prime number. Okay, so that's probably the most well-known case, and it has been heavily explored. We know all the results related to the security of using private public keys based on such groups. What's the problem? The problem is that the number theory gives attacker much better tools than the general algorithm. So the best known general algorithm takes order of square root of the size of G for the attacker. But that's the general algorithm. For specific groups, the attacker can do much better. And it turns out that for this group of numbers, the attacker can do much better. There are specialized algorithms, specialized attacks for this group. So, for example, I previously said in general case that 160-bit would already be secure. Well, for this group, a key of length 795 is known to have been broken in 2019. So 795 bits is much bigger than 160 bits, and yet it has been broken. In reality, systems using such keys, using this system of this kind of group, would be using keys of over 2,000 bits. And 2,000 bits is quite a lot. Maybe not a lot to send over the network, but it's a lot to, like, again, we need to generate keys, we need to apply keys for the signatures. And the longer the keys, the more time we take on that. So, and of course, if we include some stuff on the blockchain, the storage space on the blockchain is expensive, as we said. So you want to be as short as possible. So that's why this is not considered the best group. And this is why blockchain is not used in this group. What does blockchain use? It's using elliptic curves. Before explaining what it is, I'll just explain why it's much better. So elliptic curves allow for significant reduction in key size. An elliptic curve cryptographic key of 163 bits is equivalent to, in terms of security guarantees, to the RSA keys of 1024 bits. And if we do 256 bits with elliptic curve cryptography, it's equivalent to the RSA key of 3000 plus bits. So it's much shorter, and we are getting the same guarantees in terms of security. And this plot in this slide shows basically the benefits, or how hard it would be to break elliptic key cryptography compared to, say, RSA. Right? So here we see that that's the key size, and on the x-axis we have in terms of year of operations. So you can see that if you want to achieve significant security or increase the time to break the key significantly, then you can see that the curve for RSA is much worse than the curve for ECC. Okay, now let me again give a brief explanation about what elliptic curves are. Elliptic curves are not ellipses. It's even though it sounds very similar. So what are elliptic curves? It's a plain algebraic curve which consists of solutions like, okay, so it's two-dimensional space, right? What you see here is two-dimensional space. And two-dimensional space, and we have an equation with two variables, x and y. And it's an algebraic curve which consists of all solutions, x and y the coordinates, for the points on the solution, in which y squared is equal to x to the third plus a plus b, where a and b are coefficients. So a typical elliptic curve looks like this. Well, of course, depending on the values of a and b, they would look different. Okay, so that's an elliptic curve, but how we define operations? How do we define a group based on elliptic curves? The operation is the following one. In most cases, a line which would intersect an elliptic curve would intersect it in 3 points, like in this example. It's not always the case. I mean, obviously I can put a curve here, a line here, and then it would be no intersection at all. But or I can put it on a tangent as a tangent, right? And then it would be only 2 points instead of 3. But most lines would intercept in 3 points. Okay, so what's the operation? The operation is the following one. For example, P and Q. And then, draw the line. We find the third point, in this case minus r, and we invert it. We are finding this point at the end. Result of the operation. It's called like, if it would be denoted as a summation, it would be also called multiplication. I mean, using the plus sign, but we could use any other sign, right? Of P and Q. That's the main operation with the elliptic curve. Okay, so we also need to be, okay, there are examples. But before we come, we need to say that the actual element like it's to the curve itself. And that element is 0. So, for example, if it is R and R, so the curve would be like this. And in this case, there is no curve point. We imagine that there's like one point at infinity. And we call this point 0. So that's a special point. Okay. So some examples. P plus Q plus R would be equal to 0. Similar to this case. Because P plus Q would be equal to minus R, and R plus minus R is equal to 0. P plus Q, so here we have a tangent, right? So what do we do with the tangent? In this case, we say that P plus Q plus okay. The additional point, like the third point of the tangent, they say that it is it would be like Q itself and accordingly minus Q. So if you have a tangent, say that that the result of the operation would be minus Q. There are also similar cases, so we could go over different cases, but this is the gist. Like there are corner cases. I'm not covering all corner cases, but this is the gist of the operation on the elliptic curves. This is the geometric interpretation. There is also algebraic interpretation of all those operations, but it's more complicated, so I'm not covering it. However, any book on cryptography would also cover the algebraic interpretation of elliptic curves. So here is an example of an elliptic curve with the coefficients of 2 and 1. So for this, we can see that for this specific curve, all points would form a cyclic group with the generating point of 5 with the coordinates of 5 and 1. So I'm not showing exactly how it's computed, but you would need to trust me that 2p would be equal to 0.63, 3p would be equal to 0.106, and then if you go to 18p, then we'll get minus p, and 9p would be equal to 0. For this specific curve. So this is just an example. Okay, so this is the idea of working with elliptic curves. Now, how can we extend this to a cryptographic system? We are still working with a generalized log problem. However, instead of working with natural numbers, we are now working with elliptic curves to compute the multiplication in the logarithm. How to do it? Alex still picks a degree key, which is a secret key. And Alex takes some well-known elliptic curve. Again, elliptic curve would be known to everyone. It's like the group. And the generator of the group would also be known to everyone. So Alice takes the generator and calculates p to the degree of k, where k is the secret key. And again, it can be done. It can be done more efficiently. It can be done in time logarithmic with k. in the same way. So and the attacker would need to calculate k. However, because we are not working with natural number any longer, we are working with elliptic curves, turns out that there are no well-known attacks on elliptic curves, such as we have on natural numbers. And therefore, breaking cryptography based on elliptic curves is harder. Okay, but of course, like, there are some catches and downsides. The first catch is that not every elliptic curve is good for cryptography. We cannot just take a random coefficients and say, okay, let's try this elliptic curve. That would not work. So there are standardization institutes that research, explore different elliptic curves, and decide which one are better suited for cryptography and which one are worse. So this, for example, the NIST in the US issues verified curves, which everyone is supposed to use. There are additional downsides of elliptic curves. Some of them are patented. Some may have trapdoors. Some of the elliptic curves were developed by NSA or in collaboration with NSA. And people are a bit afraid that NSA actually knows how to break the elliptic curves. So it could tap into the communication. Also, theoretical foundations for elliptic curves is not as well developed and as understood as, say, for RSA or for the group of generated by prime numbers. So certain properties are unproven, but they seem to hold in practice. People believe them to be true, but people are not 100% certain. Still, like, the certainty is enough that the system would be used in practice, and especially used in practice by resource-constrained devices, such as IoT devices, cell phones. You also need to be a bit careful when selecting the random numbers and the generators. So that's the background on elliptic key, overview of elliptic key cryptography. Again, this is the type of cryptography used in blockchain, what generated public and private keys. Speak up, please. Oh, random number generator. My bad. Well, they all look okay. I mean, most elliptic curves look like this, but like there is slightly the stretch. Most elliptic shape, elliptic curves have this shape. And again, issued by this is what I use in the blockchain. What would depend on application? Yeah, well, again, the idea is that the key generated this way is much shorter, right? So the key size, this is the reason to go for this. This is the reason why resource-constrained devices such as mobile phones would want, or even sensors, right, would want to go for this kind of cryptography and not for RSA. Okay. The other primitive we are going to cover in this lecture, other cryptographic primitive, is hash functions. So what's the idea of hash functions? Well, the hash functions have many uses, right? So what is a hash function? Hash function takes long data of arbitrary length and produces short data of fixed length. So you can think of the hash value, so it's called like the result of applying the hash function. The short data of fixed length has many names. It can be hash value, hash code, digest, sometimes even hash itself. So the terminology is varied, but usually it doesn't create any confusion. So we can think of the hash value of the digest as a fixed size fingerprint, short, fixed size fingerprint over large variable size data. Okay. How do we use hashes? The digest may act as an identifier representing the data. So instead of comparing the data and seeing, okay, is it the same piece of data or is it a different piece of data, it would be much more efficient to compare the hash value because it's much shorter. So the digest is used in digital signatures, right? So what is a digital signature? We can take a document of arbitrary length, no matter how long it is, and produce a signature of a fixed size. And we use it for verification, right? But of course, there are many other uses of hash functions. CRC. So, for example, I download something from the internet. I want to verify that it's not fake, that it has not been tampered with, that I downloaded it correctly, right, without any data corruption. How do I do it? I calculate the hash, and I compare it with the announced hash of the data. And I see it's the same. Okay, if it's the same, that most likely that I downloaded the right piece of information. The same for messages, right? So data integrity, this is the second use of hash functions. And of course, we also use it as a keys, say for hash tables. So this is how we can store the data. And there are also a few other uses of it. It's one of the most popular primitives in computer science. Okay. But what is a good hash function? What do we exactly want from a hash function? Well, we said it takes arbitrary length for input and calculate fixed size output. Yeah? But what else? Well, we need to be able to do it efficiently as usual. So we cannot do too heavy of a computation. We want to minimize the collision. What does it mean? Usually we take large input and compact it, compress it. This is what the hash function does, into a short output. What does it mean? It means that the input space is much bigger than the output space. In that case, it means that multiple values of the input would be mapped by the hash function to the same output, or they may be mapped to the same output. That's necessarily the case because the output space is smaller than the input space. So if two different values of input map to the same output, that's called a collision. And it's not a good situation. Why? Because it breaks all the nice properties. We cannot use it. What's the use of the ID if it's unique, right? If my passport may turn out to look exactly as the passport of some other person, it's a problem. So therefore, it's important to minimize the collision or to minimize the probability of collision. So what does it mean in practice? In practice, if we assume that the input values are equally probable, there are no very popular input values and not so popular input values, then ideally in that case, we want the hash function to spread it uniformly over the output space. If, however, the input distribution look different, then maybe we need a more specialized hash function. Now, when we use it for cryptography, as we do in blockchain, there are additional requirements related to security. The first requirement is a hash function should be one-way. One-way means that it's based, like if I'm given the hash, it would be very difficult for me to to restore the original input value. So based on the signature, I can verify the signature. It doesn't mean I am allowed to read the content of the original document. Second requirement is called weak collision resistance. So what is a weak collision resistance? If you are given a hash value, it's difficult to find an input that hashes to that hash value. It doesn't mean the input that was used to produce the hash value. It could be any other due to collisions, so there could be collisions, right? Small number of collisions. But for the attacker, it should be difficult to find an input value that produces the collision. If there are collisions, doesn't mean it's easy for the attacker to find the collision. So, so why is it an important requirement? Because otherwise, I could, for example, in a file sharing system or any system that uses, say, CRC for data redundancy, or that includes some verification code in the message when sending a message, right? If someone intercepts the message and finds a different message that maps to the same hash, then the attacker could easily replace the original message and break the signature. So that's not good. The third requirement related to security is called strong collision resistance. So the second requirement was weak collision resistance. The third requirement is called strong collision resistance. And the further strong collision resistance means that it's difficult to find two inputs that hash to the same value. Now, I'll also give an example of an attack that, so if you don't have strong collision resistance, I can show you how it can be exploited in an attack. But before I do that, I want to remark that strong collision resistance is a much more stringent requirement. It's much more difficult to satisfy compared to weak collision resistance. That's because of the birthday paradox. So, how many of you are familiar with the birthday paradox? Please raise your hands. I can see. Okay, then I'll explain to you what a birthday paradox is, because many of the students are not familiar with it. Birthday paradox. Okay, so let's say I'm born on the 10th of October, which is just an arbitrary value. But now I'm thinking, what's that, like, how many people are here? Okay, let's think it's 90? You said? Yeah. I think a bit fewer, maybe 80, like it looks like 80, but that's, I mean, anyway, that's the order of magnitude. Okay. So what's the probability that one of you is born on the same day as I am? What's the probability? Well, okay, so there are 365 days in a year, and there is, like, for one of you, the probability that you are born on the same day as I is 1 by 365, and the probability that the other person is born on a different day is 364 by 365, right? Okay, now, that's for one person. But let's say you are 80 here, or 90. Then, what's the probability that none of you is born on the same day as I am? That would be that number to the degree of 90. Which I actually, like, I calculated. I think it's about 0.78. So with the probability of 0.78, same day as I am. Okay, now let's do the test. Who is born on the 10th of October? Is there a person here? Okay, no one, right? So 0.70 is sufficiently high probability. Okay. What does it mean? What's the application? This calculation is applicable to weak collision resistance. Because the attacker would need to go individually over different input spaces, right? And see if the hash value would be the same as the given hash value, right? This is what the attacker would need to do in order to break weak collision resistance. And the probability of each input value mapping to the same hash value is the same as what I did in this calculation, right? Well, depending on the space, right? In this case, the space was 365 years. It's 365 days. But of course, the realistic space is much bigger, right? So it's very difficult to break weak collision resistance. Now, I'll ask a different question. What's the probability that two people in this room are born on the same day? The calculation in this case would be totally different. So suppose, like, if you take one person, one other person, it would be like the probability of not being born on the 10th of October would be the same. But now we have two people with two different birthdays. So what's the probability of the third person to not have a collision? It would be 363 by 365. The probability for a fourth person would be 362 by 365. And so on. So it would not be like this number to the degree of 90. Each time, the probability for each next person, the probability of not having a collision is becoming smaller and smaller. And as a result, for 90 people, the probability of two of you having birthday on the same day would actually be, I believe, around 90%. So here, the probability to be successful was around 0.22, and 0.78 was the probability of the attack not being successful. For the two of you, for having a pair of people with the same birthday in this room, the probability of a successful attack would be more than 0.09, and the probability of withstanding resilience to the attack would be less than 0.1. So with high probability, two of you have birthday on the same day. Do you see how it relates to our discussion of hash functions? Can someone say? So it relates to strong collision resistance. Strong collision resistance means it's difficult to find two inputs that hash to the same value. So if there are two people, if there are two input values that hash to the same value, there's a problem, according to strong collision resistance. And the probabilities are calculated in the same way as in the birthday paradox. As a matter of fact, why is it called the door of the parallel? Because it's enough to have 23 people in the classroom so that the probability of having a pair with the same birthday would become more than a half. Only 23 people, which is a very small classroom. So this is why it's much more difficult to withstand attacks on strong collision than attacks on weak collision. All right, now, how do we exploit the strong collision? And so let's consider that Mr. Big Shot has a dishonest assistant called Mr. Creepy, and who would be preparing contracts from Mr. Big Shot's digital signature. Okay, how can Mr. Creepy launch an attack? So Mr. Creepy prepares the legal contract for a transaction. Mr. Creepy then proceeds to create a large number of variations of the legal contract without altering the important content. For example, Mr. Creepy can add a white space here or there, unnoticeable, but many variations. Then Mr. Creepy would be given the contracts, all the collection of contracts to Mr. Big Shot for digital signature, and Mr. Big Shot would sign all those contracts. Now, Mr. Creepy has all those signed contracts in his possession. Now, Mr. Creepy also prepares a fraudulent version of the contract. And as with correct version, Mr. Creepy prepares a large number of fraudulent or variations of the fraudulent version of the contract. And the contract, say, the fraudulent contract would be, say, exploiting something, doing something illegal. So, so we have two sets of contracts. And the first one would be signed by Mr. Big Shot. The second one would not. But with a big probability, there would be a pair of contracts, one from good contracts and one fraudulent contract. There would be a pair such that the hash value, the digital signature, would be the same, like in the birthday paradox. Okay, now, so that's the idea of how to exploit or how to launch an attack on strong collision. How do we implement hash functions? I don't have a lot of time to speak about implementation of hash functions. Again, there are nice books on cryptography which can give you details, but again, I'm just giving a brief overview. A hash function is typically based on internal compression function that works on fixed size input blocks. So the initial message would be broken into blocks of certain size, and the number of such blocks is unlimited, or at least can be very large. Therefore, there is no restriction on the total length of the input. And we take the first block and compress it calculate the hash value. Now, for the second block, we take the hash value from the first block and feed it into the compression function along with the second block. And the compression function would calculate the second hash value. And this way we'll continue with the next block and the next block. And the output would be the final hash value. So this is how the scheme works. So it looks like a chain block cipher, right? So produces a hash value for each fixed size block based on its content, and hash value for the previous block. And one of the properties is what's called the avalanche effect. If we just change one bit in the input, most likely all bits of the hash value would look different. So one change in the input, dramatic effect on the output. So, so this is like the theory of hash functions. But what do we do? What do we use in practice? In practice, the most popular, again, the hash function, like finding good hash function is not easy. And there are standardized hash functions that everyone is using and that researchers have analyzed and verified the good properties. So you shouldn't just come up with a hash function on your own. You should take one of the standard ones. Okay, but what are the properties of the standard ones? The most popular functions are coming from the MD family. So it all started by the MD5 algorithm, which is not used any longer. It's not considered secure any longer, but it started the family of hash functions. Okay. What you see here in this table is the algorithm, the number of output bits, the number of input bits in the block. It's like this, the size of this block. That's the number of input bits. Again, the total input can be unlimited. And each hash function calculates many rounds, right? So tries to scramble the bits, takes one round of calculation on the input block, and then does another round and another round. So the number of rounds varies across different hash functions. So here you can see the summarization about the number of rounds. And perhaps the most important is the last one, how likely the collision is. So for MD5, people are not using because it's easy to break and collisions have been found. The next sort of family of hash functions, well, still without MD5, is called SHA. And SHA, SHA, stands for Secure Hash Algorithm. So the first proposed SHA algorithm within the family is called SHA-1. And it's still in use, pretty much. It has been broken, but it's not easy to break it, right? So like a typical, but if you want to break one instance of SHA-1 hash function, then it's estimated that you need to spend an order of $50,000 on the infrastructure. So doable, but probably like a common person would not be doing that. Still, if you want to be more secure, you need to use more advanced SHA functions. So the recommended standardized SHA functions are SHA-224, 256, 384, 512. Collectively, they are called SHA-2. So the nomenclature, the naming is a bit confusing, right? So SHA-1, SHA-2. And in particular, Bitcoin is, and many other cryptocurrencies are using SHA-256. That's the one standardized in Bitcoin. As a matter of fact, there is already a new standard, SHA-3, but its adoption, it's newer, it's faster, it's even more secure, but it's not as widely adopted yet. Why? Because first of all, SHA-2 is already fast enough and secure enough, so there is no significant push to change something that's working to something that's even better, right? And the infrastructure is there, and changing the infrastructure always takes time. So that's why SHA-3 is not as popular yet. But at some point, it may replace those. So this is pretty much the end of the lecture. I would like to thank you for your attention. And even though I was welcoming questions in the middle as well, I hope to get some now.